Nuclear power hasn't changed much since the 60s, and similar techniques and reactors created then are still used today. Perhaps now, though, the future of cleaner nuclear energy is coming. Molten salt reactors were a complete idea that was shelved in the 60s. A liquid fluoride salt is the primary coolant, which also contains the fuel. The difference here from conventional reactors is that it doesn't need to be run at high pressures. It is also possible to make the reactor meltdown proof. Using thorium as a fuel for these reactors would use almost 95% of the fuel and breed more of their own. This is much less waste than current reactors. Thorium is also 3 to 4 times more abundant than uranium. Thorium is a fertile material which makes its own fissile material as part of the chain reaction. Thorium-232 absorbs one neutron and goes to thorium-233, which eventually decays to uranium-233, which is fissile. Uranium-233 undergoes fission and gives off energy and more neutrons to continue the process. As seen here, a fertile blanket which contains the thorium is in the core, and the reaction just stated takes place in the liquid fuel. If for some reason there is an emergency, the liquid salt can simply be drained from the reactor and the reaction will cease to continue as no more fissile uranium can be made. China are leading the way on developing reactors. They plan to have 2 fully functioning reactors within the next 10 years. Also, waste from current nuclear reactors can be used by certain types of these reactors. It is also very hard to make nuclear weapons from the products of the reactors, perhaps why it was shelved in the first place in the 60s. Fusion power offers the prospect of a sustainable energy source for the future, but it also presents scientific and engineering challenges. Currently in development are tokamak reactors. In a fusion reaction, energy is released when 2 light atomic nuclei are fused together to form one heavier atom. This is what happens between tritium and tritium in a fusion reactor. For the reaction to work, the fuel must be heated to temperatures around 100 million degrees Celsius. At these temperatures, the fuel becomes a plasma. Magnets are used to contain the plasma, and the invention of the tokamak does this, a Russian word for a ring-shaped magnetic chamber, as seen here from the inside. In a reactor, the neutrons generated from the fusion reaction will be absorbed in a blanket containing lithium which surrounds the core. The lithium is then transformed into tritium, which is used as fuel, and the heat absorbed is then used to produce electricity in conventional ways shown before. Advantages are there are no carbon emissions, abundant supplies of deuterium from water, and tritium produced from lithium. 1 kilogram of fusion fuel can provide the equivalent energy of 10 million kilograms of fossil fuels. Only plant components become radioactive, and these are safe to recycle and dispose of in 100 years. Due to small amounts of fuel needed, meltdowns aren't possible. However, it will be 20 to 30 years yet until we have a fully functioning power plant, but once this technology is tuned and ready, surely it must play a major role in the future of our energy. Only time will tell.